First of all, thanks for having me. I always think it's great to start with a little bit of gratitude. I'm thrilled to be able to be here and offer whatever support I can. I understand that this is probably a stressful thought of this MPT for the teachers who are here with us today. And so just as a lead off, I just wanted to mention something quickly. Some research that's been done recently, last few years, regarding the brain and gratitude. And one of the things that we often do in our classes with our students in math is tell them about these connections and the place in the brain where anxiety over a task in particular about math actually happens is the exact same spot where gratitude happens in the brain. And the really cool thing about gratitude is that if you're engaging in a gratitude practice, it actually only is able to do one thing at once. So it only works with gratitude. So it basically kicks out those feelings of anxiety. So it's something really, really cool. And it's something I thought I would share because I think at this point in your journey, there's probably a little bit of anxiety about having to write this task. We'll make it through. I feel great confidence, but that's something that's come across my table, so to speak, and something that I feel is really super highly impactful. And I felt this personally, my colleagues have felt it, and also students that I work with use this strategy quite a bit. Do no harm at any cost, but it's actually highly impactful. So I am grateful today to be able to meet with all of you. It's so wonderful to see some faces and even just to have the interactions. I actually have a lot of fun doing this. I love math and I love teaching, like I'm sure you all do. So thank you for the opportunity. OTF has been wonderful to us in the past, as I know you will continue to discover as you go through your teaching career. Just to get started, I thought that the easiest way to do that might be just to gather thoughts about the specific concepts that you want to look at. I do have some that were sent to OTF, and Ian has kindly saved those shared those with me. However, I think that since we've got more people here than what was actually shared, we're probably best to get your thoughts. So what you're going to see here is what's called a Padlet. It's probably something you're familiar with. You may be familiar with. And Ian is going to kindly send a link into the Padlet. And you will notice that when you click on that link, it will bring you to this page. On the bottom right corner of this page is a little pink plus sign. Hey, our first math, cool. And I'd like you, please, to record different topics that you think might be handy to have reviewed today. And as you do this in the next couple of minutes, I'm just gonna jot them down so that maybe it gives us kind of a place where we want to start. So if you could click that link and plop that now, that would be awesome.
I see I have support in the chat box there, so thanks for putting that link back out there again.
I'm just trying to scroll through and kind of get the gist of what is happening here. Okay. Linear systems graphically. Does this go up? Were there any other questions, I wonder as well, Ian, about the general nature of the test? Is it really up to grade 9 that they're going? Is that, is that accurate? So linear systems is actually a grade 10 concept. We can definitely look at it too. But it's maybe interpreting graphically. Actually, that's probably making sense. Let me jot that down too. Okay, so let me just make sure I've got the gist of what we have here. I know, as Ian said, we probably won't get into great detail, interior sums, into everything. But if I can click off the big ideas, hopefully that would help. And solving equations. Okay, I'm seeing that one a couple times. Okay.
And Leanne, just as we
yes.
go along, just to let folks know, if you want to place something in the chat box, I'll be monitoring that, and just if there's something that's not clear, we'll do our best there.
Perfect. Thank you. That would be awesome. Proportional reasoning.
This is just a question about Padlet, Leanne.
Oh, okay.
Asking if we can save this Padlet to look at after.
I can try to do that. I've never done that before, but I'm up for learning.
They should be able to access this with that link.
Oh,
right?
actually,
right?
You're absolutely right. I won't redo it or anything like that, so it will still be there.
I'll just include that with links in tomorrow when we send that out to registrants.
Perfect. Great idea. Thank you, Ian.
Yeah.
Thank you. Okay, thank you guys for sharing that. And as we go again, if we feel like we need to move in another direction, we can definitely do that as best we can. I did get from Ian a topic that we were hoping to discuss. And I think that was the transformations, reflection, translation, rotation idea. And so I think what I'm going to do is show you about some activities that I've created to try to address that. And that will also help you to see the different takeaways that we're going to provide for you today that can hopefully help you in your preparation for the MPT. So with respect to the transformations, the reflection, the translations and rotations, the challenge with that, as I'm sure you know, as math teachers yourselves, is that that's really a very hands-on sort of idea. So it's very difficult to try to explain that and do that without actually having concrete manipulatives with us. For that reason, I thought the best way to probably do that is to actually look at a dynamic geometry software platform. And so for that reason, I did create a Delta Math class account that I'm willing to share with everybody. And Ian actually has the instructions that you can use after our session today to actually join this class. I'm going to continue to share and show you the different little questions that I have, the different little quizzes that I've created for you, all along the top here, a variety of topics. It continues to the right, so there's lots of opportunity there. Part of my experience from a previous session was that teachers were indicating they needed some practice with fluency or fluidity of things. So these are great ones, I think, that you can use in order to increase that mathematical fluency that you might want to increase. The other great thing about Delta Math is that it will provide you with solutions. So when you go through and try something, if you don't get it right, you can click show solution and it will share that with you. So you're not going to be left high and dry saying, I don't know if I got this right. I don't know what my next step is. So it's a really powerful sort of platform in that way. The other benefit of our Delta Math is that sometimes it uses guided solutions, meaning it will show you abstractly how things are flipping and flopping and rotating, which I really do think is probably the very best way that we can explore this particular concept that was asked about. And I'll just show you briefly one of the activities. So this is one that is there for you. If you were the people who want to look at the transformations and rotations, you can see basically once you go in and register, you can have new problems, you can show solutions where my cursor is showing here. And basically it allows you to move things around and then see what's happening. And I really do think that this is the very best way that you can actually learn and explore this concept, rather than me giving you a set of rules that really don't apply because every situation is different. I think that this is probably the best thing to address that learning need. So I'll show you here. So basically it's asking us determine a series of transformations that would map figure L, so the blue one, onto figure M. And then you press try to test the transformations. So rather than, EQAO questions that you don't know whether they're right or not, this one will actually show you. So I'm just going to choose anything here so you can see. So I'm going to say a reflection over the x-axis provided by translation, and then I'll get to choose where this translation is going to go up, and then I'm going to try, I don't know how many units that's going to be. I'm going to try 10. Okay, so I just want to show you what happens. So it actually moves it for you. Now you can see that I wasn't quite successful, was I? That's okay. I can actually go back and change these things and actually try again. So I do think that the beauty of this is that it allows you to try and try again until you develop that aptitude for visualizing those reflections, rotations, and translations. Now, if you're a person where you're saying, okay, that's great, I still feel like I need to explore that in a lot more detail, and I need a little bit more structure and foundation in terms of getting to that point, I've also created a series of Desmos activities. And this is something that Ian is going to share as well. And again, I don't think we're going to go in and try these now. However, I want you to see the types of activities that are present there for you. So for the people who asked about the transformations, the translations, the rotations, specifically, there are particular activities that you can go through and work through in an exploratory way to investigate those concepts further. You can also see that there's lots of stuff on fractions, equivalent fractions. Basically, what I've done here, I've taken like a UP preparatory math program, the tasks I've created for that, as well as the grade 9 stuff, and kind of pulled them into one for you. So if you want to, you can feel free to use that as you see fit. Okay. And after the fact, if you had something in particular that you don't spot here, but you think you'd need there, or Delta Math, I can probably help you find it, or probably see what I have to support you with that. Okay, so unless you guys have any questions about that, I thought we should maybe start looking at some of these identified concepts. Any questions? Are the people who asked about the rotations and the transformations okay with that? I know yes? Yes? Okay, perfect. Thank you. Thank you. I know that I didn't do like a little lesson on it, but I really feel like that's going to do it better for you because you'll be able to see the flipping and flopping. Now, I don't think that they're allowing manipulatives on the test, if that's correct, which is a little bit silly. I'm sorry, Ian, I have to say that it's a little bit silly because really that math is all about hands-on, right? And that's how we learn best. So I think this will help you.
Leanne, we've been trying to get rid of the MPT, so we totally agree with you that we would want our students to have access to that too. So agreed. You can of course use paper as long as you're showing that there's nothing on that paper when you begin.
Mm-hmm. Something else. Oh, sorry.
That was a question that someone was asking last time.
Okay, for sure. Something else that I need to mention, just as a math educator, is that a timed math assessment is not a very good way to measure aptitude. And I mention that because I don't want us as incoming educators to feel like a fast mathematician is a good mathematician. Some of the best mathematicians take a long time to process things. I take a long time, lots of time, and I still consider myself to be a mathematician. Right. And many of my students in my 9 applied classroom take a long time, but they're great mathematicians. So I know that we're dealing with this now, but I feel like as leaders in our math communities in our schools that we're becoming, it's important that we remember that this does not in any way impact how good mathematicians we are. Anyways, enough preaching. I apologize, but I had to fit that in because it's something that irks me a little bit. So I'm looking here and I'm seeing equations, proportional reasoning. I saw a lot of linear equations, distributive property, slope. So a lot of linear stuffs and some angles and other things that I haven't quite written here yet. Since I saw, I'm thinking maybe we could start with some of the algebra, like distributive property, and then move on to equations and then rational proportional reasoning. Is that sounding okay with everyone? hopefully. Okay, so let me pop out here, and I've kind of pulled together some things that I'm hoping will be helpful for us in terms of solving equations. I think I'm going to start with distributive property, however. Let me just get the same spot here on my iPad.
Yeah, and your comments are just resonating a lot with folks here in the chat.
Oh, yes, I can see why they would. It irks, I can't, you know what, it irks me, and I'm not writing the test now. So there you go. So you can say.
Yeah,
so,
just there's a question here. Just to, do you
yep.
know if the calculator on Delta Math is like the calculator that we'll be using on the MPT? I don't know that the answer.
No, I don't know the answer to that either. I do know that they have practice MPTs where they allow you to use the calculator in practice. And I think that Lindy, or perhaps it was you, Ian, who sent out that link to the YouTube video from a person who had just taken it. And they indicated it was really important to go and practice using that calculator before the test. Yeah. Okay, so distributive property, let's talk about that just really briefly before we look at doing some solving of equations. So distributive property, I'm sure that when you guys are in your classrooms, you distribute handouts. So when we say I'm going to distribute the handout, we mean we're going to give one to everybody. Distributive property is the same. We give something to each term. So I'm going to show you, let's say I have something like 2x plus 3. If I have something like that, and I'm asked to expand or simplify or use the distributive property, it means that I'm going to take whatever is out in front and it's being multiplied and actually apply it or distribute it to each term in the following bracket. So this may be the way that you saw this presented. What it really is, or maybe another way to actually think about it, is using a box model. So whichever way resonates with you is the one I would use. I want to show you quickly the box model because I think it really helps to make it easier to understand for people who are visual. So let's say I want to do this question, 2 times x plus 3. Basically, I can create a little box model where I'm kind of finding the area of each segment, and that's actually going to give the answer to me. So if I'm trying to find the area of this part of the rectangle, I would obviously go length times width, or 2 times x. And if I wanted to find the area of this second part of the rectangle, I would go, because this is 2 units wide, 3 units long, not to scale, I'm sorry, I would get 6. So our answer to that question would be 2x plus 6. So you can choose to either just take the 2 and basically multiply it by everything that's in the brackets. That's the standard way that I would have looked at it originally. But if this diagrammatic approach helps you, then this will actually carry you on to other more complex questions as well. So maybe we should try looking at something where we have a variable out front, not just a number. So let's say I have 3x and then 2x minus 5. Let's try that one. And please tell me if I'm moving the screen too quickly, okay, everybody? If you're wanting to take notes. So I'm going to do this one using the diagrammatic approach, because that's what I find my students eventually come to like. So what would I put along, any guesses what I'd put along the width here? What is going to be applied or distributed into the bracketed expression?
People can put that in the chat. That's already happening.
That's awesome. Yep. So we've got a 3x.
Yep.
And then because this is a 2-term expression, also called a binomial that I'm distributing it into, I'm going to use those to assign how I'm going to break up that box. And I'm noticing we've got a question, distributive property versus solving an equation within the bracket. Okay, we'll talk about that. Okay, so now that we've set up our question, basically we find those little areas. So for our first area here, notice we've got a width of 3x, a length here of 2x. What would be the area inside that part of the bracket? So we've got 3x times 2x. Awesome. So we've got the 6x squared. So I feel like we're competent with our exponents. And then, of course, for the second part, we've got 3x and -5. And what would we get for that answer? 3x times -5 is -15. And the beauty of all of this is that our answer now is right there. So our answer is 6x squared subtract 15. And you can see how this integrates a couple of different concepts. It integrates the distributive property. It also assesses whether or not we can multiply a monomial by another monomial. Basically, how can we, it should be -15x. I've just seen that. It assesses how we can multiply two monomials or single term expressions together and pull it together. We'll pretend that was a test for you, that I didn't see that X, but thank you for pointing that out. It really wasn't. I actually missed it. Okay, and that's our answer.
Outsourcing answers, Leanne.
Yeah, whatever it takes, Ian, whatever it takes. Okay, so there was a question too about how do you know when to use the distributive property versus solving an equation within the order of operations or BEDMAS. Basically, this distributive property tends to be used when we are dealing with algebra. So in this situation, the two that we've looked at here, we were trying to distribute 2 times x plus 3. If I had instead something where I didn't have algebra, and I'll write this in purple instead, let's say I had 2, 4 plus 3 instead, there's a situation where could I use the distributive property? Absolutely I could, but I don't know that I would. Simply because in this type of situation, I would probably be asked to evaluate that expression rather than use the distributive property. So I do see that both have brackets to them. However, this one doesn't have any letters in it. This doesn't have any variables. So if we wanted to evaluate that, and I know you're all pretty familiar probably with BEDMAS, which means that when we're evaluating expressions, we always start with the brackets first, then we do any exponents, we do division and multiplication. That's a grouping of things. Okay, so we do division and multiplication in whatever order they are in the question. So I don't have to do division before multiplication because the D came before M, okay? It's a group. Same thing with addition and subtraction. I do that as a group. So even though it's written BEDMAS, think about BEDMAS, okay, instead. Okay, so for this type of thing here, of course, we could just use BEDMAS or order of operations. So I would do what's inside the brackets first, which was 7, and then I would get 14 as my answer once that catches up with me. Now, I want you guys to notice, and this is the beauty, the awesomeness of math, is that if I were to, instead of using order of operations as I started there, if I were to actually use the distributive property, this is so utterly cool because I could do the same thing. I could have 2 and I could have 4 plus 3 up at the top here. And I notice I'd get 8 when I went 2 times 4. And I'd get 2 times 3, which is 6. And if I went 8 plus 6, ta-da, I get 14. Is that not super cool? You have to admit that's cool. Okay, so the idea is that they're all different ways of getting to the same point. Big idea is that if it's got numbers and no letters, you're probably not going to use the distributive property. Does that address that wondering? Is that okay?
Got a yes.
Okay, we got a yes. Okay, so it's saying, what if you had a question such as 3x plus 4 minus 9x?
Yeah, 9x, yeah.
Okay, all right. So in this sort of situation, whoops, I guess it would help if you could see my screen. Holy Hannah. Okay, there we go. So with this sort of situation, I don't want to say that there are times when we're dealing with algebra where will use order of operations, where we'll do multiplication before we would do addition or subtraction. That will always happen. In this situation, though, there's nothing I can do within these brackets to simplify this. So this is a very awkward way, and this is probably a question that you found someplace as a task, and it's assessing whether or not we really understand what these brackets are doing. In this situation, as it's written, I would just be looking to group our like terms, and these brackets really don't add anything or provide any additional meaning to this. It's on EQAO. Yes, I'm not surprised. We won't even go there. Okay, so in this sort of situation, those brackets don't give us anything. Now, I do want to say, if I had something, I'm going to amend your question slightly. If I instead placed a 2, whoops, it's catching up with me here. If I instead put a 2 out here, notice that there is a 1 here, although it's implied, it's not written in. If I put a 2 here, now I would do something more. Maybe we can look at that one as well. This one here, though, basically it would be grouping like terms. So I could think about there being a 1 out here, but really it doesn't change what is inside the bracket, because 1 times 4 would give me 4, and 1 times negative 9x would give me negative 9x. So for something like this, I could really kind of drop the brackets. Okay, they're not having any additional meaning. Now from here, we could look at grouping our like terms. Are we okay what we mean by like terms? Okay, same variable, same exponent. So I would have a like 3x, negative 9x would be like the 3x. Now, something else that's important to remember, whatever sign is in front of the term belongs to the term. It sticks to it like glue. Okay, so that negative has nothing to do with that 4. That negative belongs to the 9x. So we've got our 3x minus 9x, if I pull and write my like terms together, and I've got the plus 4 hanging off the end, and I'm already seeing in our chat, we have negative 6x plus 4 is our answer. So awesome. Something else I should mention, just in case you get something like this. Now I'm going to change this a little bit. Same question, tweak it a little bit more. Right down below here. We'll come back up and do this guy for distributive property in a minute. But instead of this being 3x plus this bracketed expression, if it was 3x subtract this bracketed expression, that does have a little bit of meaning, okay? Because it's like there's a -1 here. And we're really applying that subtraction or -1 sign to everything inside the bracket. So when we manage the brackets here, we have to remember that this is really saying the opposite of 4, the opposite of negative 9x. That's what negative often means, is the opposite of. If it helps you to put it in those words, that's a good strategy to use. So this could become 3x minus 4 plus 9x, as I've already seen in our chat, which was awesome. And now we can group our like terms together. I'll put the x's together because they have the same variable and same exponent. And then people have already told us we've got 12x subtract 4 would be our final answer for something like that. So I apologize. I know I've gone a little far off there, but I just think it's important. I didn't want to just allow you to think that brackets don't matter. It really is because this was plus with nothing, which is really a 1 in front. And that is the reason why those brackets were not really impactful in terms of other stuff. Could x be isolated? Yes, it could be. And I think let's talk about equations for that. Because in this situation here, what we're doing, we are simplifying. Okay, so this is where it gets kind of funny. We see algebra and we're like, oh, let's get the x by itself. I get that because I see it all the time. But we really need to be mindful of what exactly we're being asked to do. In this situation, you might be asked to group the like terms or simplify. If I'm actually asked to find the value of x or to solve, I would need to have a different sort of question. By that, I would need to have something that had an equal sign in it. So let me pull this up. That would be an example of something that we could solve. And if I were to see the word solve or find the value of x or isolate x, that's something I could go ahead and solve for. We can practice that if you like. Notice these ones. I don't want to make you dizzy by pulling it back and forth, but notice these ones, they had no equal sign in the original question, right? They had no equal sign, so there's no way I can solve. The only way they could give you something, okay, that would be along that line, and I've seen it in the grade 9 EQAO, sometimes they might give you a shape. This is how they can integrate algebra into measurement. And let's say they're calling this x plus 1, they're calling this 2x minus 3, I'm just making these numbers up, 3x plus 4. Let's say they give us a shape like that, and they say those algebraic expressions represent the lengths of the sides of that triangle. And they say, go ahead and create an expression that represents the perimeter. Okay, I often see that sort of thing. So do we remember, we're getting to equations, by the way, I'm not derailing you there. Do we remember what perimeter means? Yeah, so it's just basically the distance around the outside. So if I wanted to find the perimeter, I would go, okay, let's take one side. So x plus 1, I'm going to take the other side. Whoops, 2x minus 3. Basically, I take my finger, work my way around the outside of the shape, make sure I got them all. And now you can see how this has created an expression that you might be asked to simplify. And here's where we would group our like terms. So we would identify, hey, we've got these x's we need to bring together. They can group together as like terms. And then we've got these numbers or constants that we could bring together. So if I were to do that, I could count up my x's. I think I've got 6 there. You can correct me if I'm wrong. 1, 2, 3, 4, 5, 6. And then if I were to take my numbers, I've got 1 minus 3 plus 4. What's that? 2. So I've often seen this where they say, okay, find an expression that represents the perimeter. And then they take it a step further. So this would be part A, find perimeter, find expression. Now, part B is often, okay, find the value of x if the perimeter is actually 20 meters long. So then they might say find x if perimeter equals 20. Now, here's a situation, and this is why I wanted to show you this one, because I wouldn't be surprised. Like, I've never written the MPT, I have to be honest, but there are so many EQAO questions like that. And if they're using that in any way, I think it's something you could be aware of. So I'm noticing here, if it tells us the perimeter is 20, can you guys see how I could then take that expression and replace my perimeter with 20? And now go ahead and be able to have an equation. Is that okay? Okay, Hillary, what was your question?
Oh, sorry. I thought you were asking us
Oh,
to see
sorry,
what we
no.
would do to solve it.
Yeah, what would you do? Let's do this one first.
Okay, well, you would eliminate the 2 on the right-hand side, so you do -2 on both sides.
Oh, beautiful. Yeah, excellent.
And then it would be 18 equals 6x, and then you would divide both sides by 6
Yep.
to isolate x.
And notice that Hillary's getting x3 equals x. It means the same thing as x equals 3, right, guys? It's just the same. Instead of saying my name is Leanne, I can say Leanne is my name. I've said the same thing, but I've just changed the order. Why divide by 6? So let's go back to what Hillary was talking about. You know why I just was like so thrilled, Hillary, is because your thinking behind this was so awesome. Because you're undoing the operations. And I think that's a really critical thing. Now, some of you may have been taught or may think about it as moving something to the other side and changing to the inverse operation. And that's an okay way to think, but it does have a couple of potholes that cause problems later on. That's why this way of thinking about it is really helpful if you can. So we know we're trying to get the x by itself. And so we had the x connected to the 6 by multiplication and connected to the 2 by addition. So Hillary started with kind of like the loosest connection, the addition, and she undid that. So she subtracted 2. And then once we got here, there was a question about that. The 6 is connected by multiplication. When something is, a number is right in front of a variable and there's nothing written in between, multiplication is implied. So to undo that multiplication, that's why the division happened. So she divided this side by 6. Since she divided one side by 6, she had to divide the other side by 6. I'm not sure about our level of familiarity, but an equation is like a teeter-totter. And basically what we do to one side, we need to maintain the balance on the other side. Otherwise things go haywire. So it's easy to remember it like that. What I do to one side, I do to the other because it's a teeter-totter. I undo operations. Now, we already talked about BEDMAS. And we know that BEDMAS always does the multiplication division before the addition subtraction. When we're solving an equation, we're basically undoing a connection. So we go opposite order of BEDMAS. So we'll notice that we undid the +2 before we managed trying to undo the multiplication. So when you're solving an equation, it's going to go in the opposite way. And that's why we start with those. I don't know if this sounds kind of hokey, but the way we think about it is that, let's say I have a necklace and I have a knot in my necklace, or if you're a fisher person, you've got a big ball of fishing line that's all tangled up. If I'm trying to undo that knot, I always start on the outside, the loosest knots, and I undo those first. And then I'm much able to get to the tighter knots, and they're always last. If you think about this equation, the +2, it's further from the X, so it's like a looser knot that I'm going to untie with the inverse operation before I get down to the closer one. Okay, so let's see. There was a question about decimals and fractions. It shouldn't matter if it's a decimal that's or if it's a fraction or a decimal that's an exact decimal. And I'm wondering if your test is going to be specific relating to that. For instance, if I had a fraction of 1/3, 1/3 is the fancy schmancy math name. It's an irrational, it's a non-terminating but repeating decimal. So if I type this into my calculator, I get 0.3 and it goes on forever and ever and amen. So if I were to write 0.3 as the answer, I'm probably being pretty accurate. I'm not sure what they're going to say with regard to that. If I write 1/3, I am like absolutely precise. Okay, so I'm thinking that we want to try a couple more equations. Do you let me pull some up here, if that's okay? And because I'm seeing lots of questions with equations and one with fractions too. So let's look at that.
Leanne, if I can just jump in here for a second, just to mention to folks that Leanne and I were having the conversation before the session started, and unfortunately, OneNote, she's not able to share that outside of her board. So this won't be among the links and resources that we're able to share with you tomorrow, just so that you're aware. That's beyond Leanne's control.
Yeah, unfortunately, I'm sorry. And I was really bummed about it, to be quite honest with you, because I made these up before and then I went to click share and it was like, it wasn't sharing for me. Now, do we want just practice with this, everybody? Or would you actually like to see some diagrammatic representations of equations? Like, I'm just wondering how much we feel in terms of support. We just want to practice, or
just let us know in the chat there with a yes.
Okay, I'm seeing practice. Perfect. Okay, so we could start with a couple of these right here. So why don't we try? Do you guys want to take a moment to try it?
Yeah, we've just had a request in the chat about not moving ahead too quickly with the answer in the chat box. That's helpful to allow people the processing time to think through on their own. Thanks.
Okay.
Can I just ask a quick question?
Sure.
So I was one who asked about the fractions and the decimals. I guess my question is, I'm pretty sure that the math test is all multiple choice. Is that correct?
I'm not sure. Ian, do you know the answer to that? I think it is. That's what I think I've heard.
Because yeah, that was why my question was like, if I got a decimal because it's a fraction, like x equals 1/3 or whatever you said,
Right?
the answer I guess would be like on the multiple choice. If it says 1/3 or if it says
Mhm.
0.3, then I would know which one.
Right, right.
Okay.
And I would choose 1/3 if that were the option.
Oh, I see. Oh, hopefully they don't give me both because that's not fair, but
I don't think they would. I don't see how that would really get to any sort of,
yeah.
valid point, to be honest.
Okay, perfect. Thanks so much. I just sometimes you never know, like sometimes teachers want the fraction or the decimal and it's just kind of
Right.
confusing.
Right. I think the general rule of thumb, it depends on the context, obviously,
Yeah.
which is what you're saying. But the more accurate is generally the fraction. It's exact. Whereas lots of times if it's like a non-terminating, meaning non-ending decimal, that it's an approximation. So I guess it's on multiple choice, so you're not going to be able to add in any sort of symbols or whatever, but there are ways in math that we can show that something's an approximation, like using a little equal sign with a dot on top shows
Okay.
that and communicates. Whoops, it's not showing up here.
Sorry, go ahead.
Yeah, go. And this communicates, this sign here communicates that is an approximation.
And Valentina, you're absolutely right. That's how the multiple choice tests work, right? Is to give you common errors or distractors.
Mm-hmm. Okay, thank you so much. It's really helpful.
You're welcome. Okay, so can I have a thumbs up, or are we ready to go through this one?
Can I answer the first one?
Okay, go ahead.
Okay, so we have like -3 minus 5d equals 17. So if we move -3 to other side, we're gonna be 17 plus 3, which is minus 5d equal 20, right?
Okay, so let's just see that for just a sec. I just want to make sure we're okay with that before you continue. Notice that she spoke about moving the 3, which works awesome. Okay, awesome thinking. I'm going to write in the +3 so that you guys can see we're still doing the same thing to both sides. And the reason why we don't really need to write it in on this left side, because the -3 and the +3 actually give us 0, right?
Yeah, yes.
So that's why it's not necessary. Anyways, I'm sorry to interrupt. Go ahead.
Okay, then we have minus d equal 20.
Okay.
Then d equal 20 divided by -3, which is -4. That's the answer.
Awesome.
Thank you.
Thank you.
No problem.
Now this
Could you repeat, please, for me?
Yeah, sure. So we started here. We noticed that there were a couple of connections. Now this one is a great one because it changed the order. Lots of times we see the letter written first. So I'm going to write it down below. And this down below where it's coming up, maybe the way you're more comfortable seeing it. But our participant here really was still able to see, even though it was written with the constant or the number before the variable, they were able to see what the connections truly were. So we have a subtract 3, and we've got the -5, since it's right next to the D, it's connected by multiplication. So I'm always going to undo the addition subtraction first, whatever the loosest connection is. So since this was subtract 3, she added 3 to undo that. Because we added 3 to the left side, we also added 3 to the right side. Now, the way she thought about it was just say, okay, I've got to subtract 3. When it comes over to the other side, I add 3. That's perfectly good. Okay, but I just want to make sure that you understand the why behind that little trick working. Notice the -3 and the +3, they became 0. So we were left with the -5d equals 20. And we noticed that the -5 is connected by multiplication. So multiplication is in there. And I'm just going to write that so that we really remember that's important. And I was actually pretty impressed that when you chose your next step, you realized it was -5 that we would be dividing by. Because -5 is multiplied, therefore -5 is what we divide by. The one challenge with that idea that we talked about at the beginning about moving things over, when we get to situations just like this, some people say, hey, that's a -5. How come it's not +5 on the other side, which is a major misconception, because the -5 is actually connected by multiplication. To undo multiplication, we need to divide by whatever we multiplied with. And since we multiplied by -5, it is the -5 that we divide by. So, oops, I should have written your answer, and D equals -4. Are you guys okay that you can always check your answer to make sure that you got them right? So you could take your answer -4, pop it back into the original question. And if your left side equals your right side, you know you're good to go. So you know whether or not you know those things before you even leave that question. That's the beauty of equations.
Thank you so much. Appreciate.
You're welcome. Okay, here's one with had a fraction in it. Can we try this one now before we go forward? And then we'll make sure that we try to cover other things too.
We'll just ask everyone not to put the answer to that in the chat again.
Okay.
As a reminder, until you're ready.
Okay, sounds good. So let's take a minute or so to give this one a go. Okay, so what do we think?
I can try.
Yeah, sure. Sounds
Okay.
good.
So you would remove the 7 first from
Okay.
the left-hand side. So because the 7 is a positive, you
Okay.
make it negative. So
Okay.
7 minus 7 on the
Yep.
left-hand side. -4 minus 7 is, I think that's -11.
Yeah, awesome.
And then so you have z/3 equals -7. I think what you do is you multiply the 3 on both sides.
Yeah.
I'm not completely sure. Okay.
No, you're absolutely right. Because you're following along in that thinking of undoing. In this situation, we notice the 3 is divided. So the connection is division. So to undo that connection, you multiply, just like you said. And since we multiplied by 3 on the left side, like you said, you multiplied by 3 on the right side too. Notice that the 3 and the 3 here, 3 divided by 3, anything divided by itself ends up giving us 1. And that's why we have Z. We finally isolated it. And of course, we've got our -33 over there.
Can I add some comment?
Yeah, sure.
Like for the last question, we just do cross multiplication, right? So
No,
you can't do that?
No, you can't. You can't. Cross multiplication is like one of those tricks that some people use to solve proportions. I'll show you a situation where people sometimes use cross multiplication. Let's say I have x/3 equals 9 over, trying to get one that's going to work for us here. It doesn't matter, even if it's a decimal.
Just put any number. Yeah.
Any number. Okay. So if I had something like this, x/3 equals 4/5. Some people use something that's called cross multiplication. It's really just kind of like one of those tricks that people use. Notice this is different here because this situation, and I'll circle it in green at the bottom. Can you see that this is what we call a proportion? Because I've got a ratio over here or a fraction over here and a fraction over here. Take a look at this original question. I don't just have a ratio and something else. This is not just a straight, like we've got the addition that's happening here and other stuff.
But still we have, like, if we put it like -11 is over 1. So we can do cross multiplication.
Sure.
Right?
Once you get to that point, yes.
Yeah,
I thought you meant right up here.
Yeah, we can do that. Okay, thank you.
You're welcome. A challenge with it is make sure that we understand why that works, just so that it doesn't catch you up. Just like with this kind of stuff here, sometimes it works sometimes, and then we have some challenges with it. Okay, do we feel like we're good with equations, or shall we go on and maybe look at some linear stuff? Is that okay?
This is good to vary for me.
Yes.
Is it possible that you could show us how to do the cross multiplication? I don't use it yet, but I'm curious how people do that method for the fractions.
Okay, so I'm going to talk about that, and then I think we're going to go on to some linear stuff.
Yeah,
So
we've got lots of yeses in the chat box there to move on to linears there. So.
okay, perfect. Yeah, I think that's a big idea. So let's talk about the ratios here. Let me pull this up. It's basically dealing with ratios and proportions. For some reason, this is showing, this hasn't synced to my new one here. Yeah, for some reason on my screen, it's showing, oops. Okay, my apologies. I'm gonna have to scroll down a little bit. We did this with somebody else, but it's not really syncing with my device. So let me just see here. Okay, so here's a situation where this is what we call a proportion. So in this case, I've written it as a ratio rather than fractions, but you can obviously write it as fractions as well. So I'm going to do that right now. So there's this little trick that people call cross multiplication. It's actually not a mathematical process. Okay, it's one of those tricks which we just need to be a bit careful of. And what people do in cross multiplication, it's basically they cross like this and they multiply across, just like cross multiplication sounds. So in this case, they would multiply the 11 times the 32, and they would multiply the 8 times the m. And now we have a little equation that we could go ahead and solve. So it basically gets rid of the denominators. Now, if you remember when to use that, that works out great. I'm going to write this down again, and I'm going to show you that there are other ways to do this. So if you're not comfortable trying to learn something like that, not sure when to apply it, you can actually use proportional reasoning to find these answers. So I notice that I've got a fraction and another equivalent fraction here. I can notice that there's a connection between these fractions if they're equal. I can notice that, hey, 8 times 4 actually gives me 32. So therefore, I know that if I'm doing that to my denominator to create an equivalent fraction, I would do that to my numerator as well. And so I could find that the value of m was actually equal to 44. Is that okay? So there's many options, okay? But the cross multiplication would be like this. So what's 11 times 32? 320 plus 332. What is that? 342. Can you check? I don't have my I should have brought my calculator.
352.
352, sugar. So 352 equals 8m. And now, of course, from there, I could go and divide both sides by 8 and solve that little mini equation, and we'll get the same answer that we got over here. So divide by 8, divide by 8. And so we'll have m equals 44, just like we got looking at the proportional reasoning. Okay, so both work for sure. Now, the advantage of this approach, really what you're doing in this approach, I know we don't have time to discuss it, but you're really multiplying through by the same thing. You're actually doing solving of equations, and you're multiplying by 8 first, and then you're multiplying both sides by 32 first. And that's the reasoning behind why it works. Just be careful, using it. Is that okay if we go on to linear now then, everyone? Just because I want to make sure we get that.
Yeah, you'd had a lot of yeses.
Yeah, thank you.
Yes, yeah. Okay, you're welcome. Okay, so now looking at this, I have a visual pattern that I thought it might be helpful for us to see. And you can see how it actually connects to slope and y-intercept and all of that kind of stuff. So I'm just finding this here. Visual patterns, Desmos. Here we go. So I don't know if you really need to copy this right now, but I think it will help you to kind of see how this all connects. And I definitely actually think it's worth our time to look at this really, really, really briefly. So lots of times when we start looking at linear patterns, we look at step numbers and we look at algebra tiles. I know you're not going to be allowed to use the algebra tiles in your test, but I think it's really imperative that you understand what we mean by slope and what we mean by vertical intercept or y-intercept, or all of that y equals mx plus b form that people have been asking about, because once you understand what it really means, it makes so much more sense and it's much less anxiety. So I just have these visual patterns here, and I could create some step numbers that would actually represent my x coordinate, and the number of tiles that are there is really like my y coordinate when I want it to actually plot that. So I'm noticing in step number 1, I've got 5 tiles. Step number 2, I have 7 tiles. And notice that I am counting all of them as a single step. I've colored them differently just for the purpose of seeing something as we go forward. Step number 3, I've got 9. What would I have for step number 4? Can anybody
11.
You have 11. Awesome. So notice that this thing is increasing by 2 each time. So for every step, it goes up by 2. And if I wanted to plot this, I could. But I noticed that my graph down here doesn't start at 1. My graph actually starts at 0. So I would like to have a step 0. Can you predict for me what step 0 would actually look like? If I were to go back, yeah, you got
0
it. Right?
and 1?
Yeah, we were going to have just 3.
0 and 3.
Yeah, just 3 of those dots. We notice that as we increase by step number, it's increasing by 2 each time. That means if I wanted to go back to step 0, I would actually have to decrease and I would get 3. So I can see it visually here. I'd have 3 because I'd be going back this way. But I can also look at a table of values like we have here and see that I can just extend the pattern in the other direction. So I want you guys to notice here that what we're, let's actually draw a little picture here. So we're starting at 0, 3. Step number 1 had 5. So I can kind of just go through. I'm going to quickly draw this for us so we can see it. It's going up by 2 each time. You guys already told me that. And I could extend my idea here. So when you guys get questions and they ask about initial value, they mean where it starts. It's like step 0. So our initial value in this sort of situation would be 3 because it starts at 3. If I'm looking at something like y equals mx plus b, the whole idea of b, why they chose b, I don't know, but it just means initial value, okay, or where it starts on the y-axis. Now, by multiplier, we often use multiplier because if we're describing a rule, so if I was trying to look for the number of tiles, I know I'm always going to have 3 tiles, but with every step, I actually add 2 more. So if I wanted a rule, I could say the number of tiles would be starting with 3, and then every step I add 2 more, so 2 times, and if n was like the step number. So I want you guys to notice that in my rule, can we see that 2 is actually multiplying by the step number? So the multiplier is what we multiply by in our rule. It's also the amount that it increases with each time. Another way of thinking about that, it's the amount that it rises, so it goes up to every time it goes over 1. And I can actually draw that into my picture. It goes up to over 1. So basically, the rise divided by the run on this picture, are we okay that that would be 2 over 1? Does rise over run look familiar to you? Okay, good, because that's the slope, right? When we're talking about rate of change or we're talking about slope, that's what it is. It's the rise over the run. I want you to notice that that's the same thing that it's going up by for every step. And that's also the number that we multiply by. That's why we call it the multiplier. That's another reason why in y equals mx plus b, it makes sense to call that number in front of the X the multiplier or the M value. So this is the multiplier or slope. Now, once we do that, once we identify that, it makes it easier for us to graph lines once we know what the multiplier and slope are. So if I were to give you an equation that was like 2 over 3x plus 5, whoops, something like this, we could be able to identify the y-intercept or the initial value. And we could also identify the slope, and we could use those two pieces of information to actually plot this line. So we can compare it to y equals mx plus b. So what would our initial value be then? What would that be for this equation, for this line?
Good folks.
Yeah, it would be 5. Awesome. And then our m, or our slope, is 2 over 3. And remember, that's the same thing as rise over run. So the beauty of this, I don't know if you're going to be able to see my grid paper as I create it behind here. It's not showing, but I'll be able to kind of draw it on here so it's less messy. So let's say I have an axis here. And I could actually use this information now to actually graph this. Whoops.
Yeah, so after you've done that, maybe you could just do just a quick review of what you've done in the steps there.
Yes.
Thanks.
Okay. Yep. Actually, we can pause here. Let me look at the chat. Okay. Can you back up a few steps for sure? Okay. So I'm going to back up a few steps for people who are who don't want me to back up. Perhaps do a little sketch and try to graph this line using the information that we've provided, that we've identified, that the slope would be 2 over 3 and the y-intercept would be 5. Okay, so let's go back here a little bit. So the purpose here was for us to see that the y-intercept, or what we call the initial value, is where the graph starts on the y-axis. We want it to kind of make the connection that initial value, or y-intercept, is actually representative of step 0 in a visual pattern. So there's so many connections here. But part of what you might be asked, the EQA and the grade 9, is about the connections. That's why I think it's worthwhile. So I could find, so this multiplier or the slope, we notice that it's rise over run. We can practice that in a minute if we like. We can find that from the graph. So I could take any 2 points on the graph and move from one point to the next and figure out how much I rise and how much I run. And that would give me my slope. In the y equals mx plus b, that's what m stands for. It stands for slope. I want you to see that you could get that from a graph. If I was looking at this table, I could also get that information, because I notice that it's with every one step that it's increasing, it's actually going up by 2. So it's rising, going up by 2 for every one it goes across. So there's another way that I could identify the slope. So y is always up to the sky. Okay, y is always to the sky. And we can write this as y equals, which is what we did below, plus 2x. Okay, I used n here because we were calling it step number. The variables we use, I'm sorry if that messed us up. The variables we use are kind of interchangeable, so you might see different ones, albeit you should see the same ones in the single question, right? So the one that's the y, whatever's on this side by itself, that's what we call the dependent variable, and that's the one that's like to the sky, the y-axis. Okay, so whatever value is being multiplied by your variable, and it might be X, it could be N, it could be anything depending on the context of the question. Whatever is being multiplied is your slope. That's what you need to remember. And that's why we call it multiplier, and why we often use the letter M to describe it, because it's going to be multiplied. The number that's added or subtracted really is the number that's the one that's off by itself without the letter is your y-intercept. I'm sorry about that if that N bugged you. Is that okay? Are these any other further questions about that stuff? And they should let you know what the variable is. Yeah, like they'll probably have a question that'll say, you know, plot this versus this, where N represents number of hours worked and C represents cost, something like that. So instead of using X and Y, they might use C and N, but it will still kind of, it should still make sense for you. They'll write that out. Okay, let's just try this one. And then I think there was something else we needed to chat about. So using this idea, were there ideas about how we could go ahead and graph this line? Where did you start anywhere? Okay, so
Pop it into
yeah,
the chat if you need
yeah,
to.
they did it. So they said 5. So that's exactly what we do. We will start with 5 or 0, 5, as we're seeing it written there. Awesome, using coordinate geometry. So we're starting at the initial value, hence we initiate our drawing like that. And now we're going to use our slope in order to generate another point that lies on our plane. So our slope here is 2 over 3. So basically from our point that we know lies on our line, I am going to rise to 1, 2, run 3, 1, 2, 3. So I'm going to rise up to run 3, and I'll get another point. And that one on my graph ended up being at 3, 8, I think. Oh, no, 3, 7. Sorry. If you could see my grid, I apologize, you can't, you would be able to count them. You count them, we've gone 1, 2 up, 1, 2, 3 over. I basically just use that. And now we have 2 points. That's really all we need in order to draw our line. And even if you have a Cartesian plane, like an XY axis that extends left and right, you can just take your ruler or, you know, descriptor and just kind of extend it to the left. Because once you've got the 2 points, you're good to go. Okay. Linear, do we want to look at, I'm finding this here, slope, or let me check back to my original stuff here. I just want to make sure that we hit on the big ideas. I know that there was a question about measurement. Was there a question about Pythagorean theorem?
I don't remember seeing one in the chat.
Pythagorean. Okay, no problem. I do have some other problems. I'm being asked about word problems. I have some here I can share with us. Oh, distance, time, and speed. Okay.
Yeah, I'm just watching time too. There's 20 minutes remaining. Just
okay.
Track.
All right, perfect. Thank you.
No worries.
Okay, so let me just peek through here. I think I might have what I tried to do. I actually spoke to a student teacher that I had a little while ago because she has just written the MPT, and I asked her what I should do, and she suggested that I create these "what would you do" questions. And so that's what I have here. I don't have any distance time graphs on them, but I think we can tweak it to make it happen. And distance, time, and speed. Actually, we can make that happen. For some of these. Okay, so let's go ahead. I was just checking to make sure, and we can decide which ones we want to do. So what I've done in this section is, and I could probably download this, but these are just from the internet. I went into the old grade 9 tests for EQAO, and I just kind of randomly selected questions in order to use. just to practice. So here are some word problems that we could use. Let's try this bit first, and then we'll go down to a distance time one. So here is one that was actually asked in our grade 9 applied EQAO several years ago. So a sailboat is pictured below. Each sail has a height to length of base ratio of 3:2. And it's asking if the height of the sail is 9 meters. Basically, we're asked to find the length. I mean, there was multiple choice, but I actually made it into just a real question that we could try. So this is a situation where we have a ratio. So you're trying to read what's there and create a ratio. Now, one of the most important parts in terms of dealing with ratios is to make sure that we're clear about what represents what. So this ratio or this question relates height and length. And I know I saw the little 3:2 there. So that was like the hint to me, hey, this is a ratio, red flag. And I'm noticing that it's height to length. So I'm actually going to write it as a fraction. Instead of writing it as height to length equals 3:2, I'm actually going to write it as height over length equals 3/2. Okay, so the hardest part is probably just figuring out what kind of mathematics we can use to model that problem. So it's telling us that the height of the sail is 9 meters. So this is why it was really, really important to kind of establish how you were going to set up your problem. I say that because if we don't know that height is on the top in our solution and length is on the bottom, then I don't really know where to put this 9 in. But it's saying the height of the sail is 9. That would mean that wherever height is being represented, I'm going to replace it with the 9. Once I do that, now I have a little mini equation, a proportion that I can go ahead and solve using the strategies that we have. So I'm hearing in the chat that we could multiply the 3 by 3 to get 9. So it makes sense that we could also multiply the 2 by 3, and therefore we could figure out that the length would actually be 6 meters when we had a height of 3 meters, because it would be in that same ratio.
Oh,
Now,
sorry, can I talk?
Yeah.
And also we can do cross multiplication, right?
You could do cross multiplication there, yes. Yeah,
Okay.
it will work for sure. Okay, oops, I'll leave this here. I'm sorry, I didn't mean to rush. And then I'm thinking maybe we take a look at.
If I may ask a quick question, how did
Yep.
we know to put the height on the top in this scenario? Is it because the base ratio? I guess I'm just wondering how we know the 3 is on top as well.
Great question. They told us that it was height to length was this 3:2. So when they said, they had to tell us that. We wouldn't have known otherwise. They said height to length was 3:2. So that meant that that had to represent height and the second one had to represent length. So in a ratio, if you need to be told that, you can't just assume that one is the other. They could have similarly said the ratio of length to height is 2:3. They could have said that instead. And if they had done that, then we could have simply, flipped both sides. So we could have had height length equals 2:3. And then we still would have known the height is 9. Then we would have put the 9 in the bottom. So it's really, to answer your question, all relative to how they are presenting that to you. So it's just a matter of reading it carefully. When they give you the order here for the ratio, that is referencing the order that they are listing the terms of your ratio.
So the first term is always going to be on top. The second term will always be on bottom in the order they give it to you.
Yes, you can. It will always be the order that they're listed here. Yes.
Okay.
Yes.
Thank you.
You're welcome. Okay, so I'm gonna just scroll down here a little bit. And we have some ideas. So we had distance time graphs. I don't know if I have one of those specifically. Let me pull something up right now. I will get it for us. Because we can do rate of change and whatnot with everything else, but I am going to just pop in here into my grade 9 class because we've done distance time graph and that will help us with the question.
It's like you've done this before, Leanne.
We all do this every day, don't we? Okay, once this just syncs for us, let me just find it in here. Cycle 1. Yes. Trying to find one that we could practice here. Okay. Okay, so content library. Sorry, guys, it's just syncing, but I promise we've got lots of distance time stuff here. It's probably worth us looking at since that has been something that has been asked. I'm just erasing my notes on it so it doesn't kind of give it away for us.
Well, Leanne, you're among friends here soon.
I know.
You're going to be
I know.
patient.
Okay, thank you. I feel quite comfortable. I was just kind of waiting for it to. Cycle 1. This is the notebook that my students have. Okay, it's coming. Distance time graphs. Oh, sugar. It's being temperamental, Ian. This is annoying. Cycle 1, page 10. Okay, it went to the very top one. We're coming. We're there now.
What did we say before we began, Leanne? Technology is our friend until it isn't.
You're absolutely right. Okay, here we go. And this is going to, it's not syncing. This is a little disappointing because on my device, it's actually stopped. It's actually erased here. Let me find us another one because it's just not doing it quickly enough for my liking. Okay. Oh, I know. I got another option. Okay, I'll go into the teacher only one. These ones don't have notes written on them. Okay, cycle 1. Should have done that in the first place, heavens. Okay, there we go. All right. Oh, you can't kidding me. You're kidding me.
Can't win.
Oh my, I can't win.
Yeah.
Okay, it's coming. It's coming. We'll find this. Oh, good Lord. Okay, 11. Try 11 instead. Okay. God willing. Okay, yes, thank goodness. Okay, here we go. So here's an example of a distance time graph. And we could use this graph to describe motion and speed, which is what the question has been about. You'll notice that distance is on the y-axis or the vertical axis, and speed, or sorry, time is on the horizontal axis. So this was distance in meters and time in seconds. This is something we practice with our motion sensors at school. So what we can do with this is look at each section and see what it tells us about the motion that's actually happening. First of all, just looking at that, can anybody predict what is happening in the motion, what the speed would be during that middle segment that we have there? Any ideas?
Zero.
Yeah.
Pop that into the chat.
Yeah.
Euro slope.
Speed
It's
is
constant.
constant. Yeah, it's
Yeah.
constant, but it's also 0, which is really important. So if we're trying to find the speed on a distance time graph, I want us to remember that slope is the same thing as rise over run. We've said that a couple of times. And so for each section on this graph, if we were to find the rise and the run, the rise would be indicative of the change in distance. So it would be like change in distance. And then the run, or the distance across, because the x-axis is across, that would represent that run would represent the change in time. So in this idea, the rise over the run would in fact give us change in distance over change in time. So like meters divided by seconds, or the speed. So the takeaway from this is that if you are on a distance time graph, speed is the same thing as slope. So if we wanted to find the speed of, we can call this segment A, that would be equivalent to finding the slope of segment A. So I could write slope A equals, and now I could look at what the rise and what the run would be. So I notice on my graph, I might have labeled only every second tick, but I can certainly go in and fill in those values that aren't labeled, and that can help me quite a bit. In fact, that's a good strategy to use if ever you are, trying to make sense of something like this. So it's catching up with me. So if I wanted to find the slope or the speed in this first section A, I notice that I'm starting at 3 kilometers and I'm going 6 kilometers away. Are we okay that my rise in that situation would be 3, meters, not kilometers? Are we okay that that rise would be 3?
Yes.
Okay, rise 3. And we notice that the distance across, or the run, notice that the run would be 3 seconds. So I can replace my rise by 3, my run by 3. And then if I were to simplify, 3 divided by 3 gives me 1. And I know my units would be meters per second. So we can see that the steeper the line that we would have, the faster the speed that's being represented. Now, this middle part, you talked about, let's call that B. If I wanted to find the slope of B, you already told me that the slope was 0 there. Makes sense, because if I'm looking for the rise is 0. It's not going up at all. The run is still from 3 to 6, so the run is still 3 seconds. But even if I go 0 divided by 3 meters by 3 seconds, I'm still going to get 0 meters per second. So basically, these distance time graphs completely tie in with our notion of slope, which we originally called the multiplier, which are all of those different things connected together. Now you could find the last one here. Now, oftentimes when they ask you this stuff, these are like graphing stories. So they ask you to describe what's happening. So for this particular graph, they might tell you this is about a person's distance from home. They start at school, go someplace, and then come back home. So my story might be, I am starting at 3 meters from home. I'm meeting my friends. We go and we walk together for 3 seconds. After 3 seconds, we pause and tie my shoe for another 3 seconds. Now I say, oh, maybe I've forgotten something back home, so I need to go back home to get it. And that's why I'm going back here. So you might be tasked with creating a story, or they might give you a story and you ask to describe it. One last thing, can we look at Ian, this very last bit here, segment C?
Yeah, sure.
So segment C, if we wanted to find the slope of that, I think you guys are going to notice that instead of going up to the right, that's going down to the right. So we tend to say that that is negatively sloped.
6.
Right. And if we're going to start here at the leftmost portion of segment A, I notice that as I'm going from left to right, I'm going to go down 6 units. So my rise, I guess I could think about it as negative 6 meters. my run, still going to the right, is positive 3 seconds. So that's why that's negative. If I were to evaluate that, negative 2 meters per second. So if it's up to the right, it's positive slope. If it's down to the right, it's a negative slope.
So with that, I'll bring the session to an official close, and with thanks to everyone for joining as well. So thanks so much.
Thank you, Ian.